The next type of force, and again this is part 2 of my types of forces videos, the next force we're going to talk about is friction. There are 2 types of friction. We use different notation to make it clear what is what, and we will be covering this next week, so this is the second half of chapter 6, gets into this in detail. So right now I'm giving you the idea, later we're going to calculate it. So the first type of friction, well, let me say in general what's true about friction. Friction is always between an object and some sort of surface. And there's some motion between them, or there could be motion between them. So in this case, there is a sled, which is our object, sliding on snow or ice, whatever the surface is. So there's motion, relative motion between the ice and the sled. The force is going to be parallel to the surface. Now obviously in both of these situations we have a flat or a straight line surface. If you imagine some curvy surface, it's going to be parallel to the point that the object is in contact with. That's a nice simplification. So now let's talk about the 2 types. One is called kinetic friction, where kinetic is a word we will use a lot in physics, and that relates to motion. And in this case, you have an object that is actively in motion. It is moving with respect to the surface. And this with respect to the surface is the important part. The symbol we use for it is F, and typically for friction, we use kind of a curly lowercase f, or just lowercase f, and we use a K subscript to represent kinetic. So you could also write capital F, meaning force, sub F and K, but we're going to start adding other subscripts, so it's really just nice to use a lowercase curly f to represent friction, and then sub K or sub S to represent kinetic versus static. So kinetic friction opposes the motion. You have an object that is sliding against your surface. Kinetic friction opposes the motion, i.e. it slows it down. Static friction is when an object is stuck on a surface, and it doesn't mean stuck with glue, it actually means in a way stuck due to the friction, and it prevents the object from sliding. So you have static friction in the case where your object could be moving if there was no friction, and so you wouldn't just necessarily have static friction of like a pen sitting on a perfectly flat horizontal table. But this frog is on a ramp but isn't sliding down the ramp, so we say that static friction is what's kind of sticking it there, and it opposes the sliding. So the frog would be sliding down the surface, so we say that static friction is up the surface. And again, we will return to this since friction is a big topic in a few sections from now. So you will see more about this later. The important thing right now is to just have a sense of what the notation is, and again, kind of what the names mean. Okay, drag. Drag is probably my least favorite force. Second least favorite force. And drag, you can think of this as friction with, say, air or water. Normally, the only drag we talk about in this class is air resistance. And the other type of drag would be water resistance, or drag just in water, in a fluid. And it points opposite of the motion. So if you have a leaf falling, we know that gravity is acting down, but we would say that drag is acting up. And this is actually really complicated. The book does go through, again, later on, how to calculate this, and that's typically a section that I skip. That it's really hard to do a good job simplifying situations. It depends on a lot of parameters. So in general, I would just rather not talk about it. Now, if we're not talking about it, that means that it needs to not be important. In a leaf falling, there's actually a lot of drag. We really would need to think about that. But if I just drop a tennis ball, there's not comparably very much drag. So when we say that air resistance is negligible, or for most of the situations we deal with, we can look at it and say, yeah, air resistance is negligible in this situation, then we don't have to worry about drag. So one of the reasons I don't care for it very much is that it makes everything super hard to deal with, and I would be very sad if in my everyday life I had to think about calculating air resistance. So I think thrust is probably my least favorite force, and only because it confuses students so much. That's why I don't like it. So again, there's not really a great way to write it, just put the whole word in the subscript, I guess. And part of why I don't like this is that a lot of students start applying it to situations when it doesn't exist. So for instance, if a tennis ball has been hit by a tennis racket and is traveling over the net, there's no thrust force. Don't tell me there is a thrust force. What's important here, and this is where we go back to the agent and object model, there needs to be an agent. So in general, this is a recoil force, and we'll talk later on about what that means in like chapter 7 and 11. So it's a recoil force, but the point is there's a second thing in our picture, which is the agent. So for the rocket, the thrust force is exerted by the exhaust on the rocket. And if you don't think that makes any sense, you have no idea what I mean, don't worry, we'll talk about it more in chapter 7 and 11. But the point is, if a tennis ball is just moving through the air, and you say that there's a thrust force, well, there can't be. What is the agent at that point? There's nothing that it's actually interacting with. And it is more or less a contact force. Again, this exhaust is right here with the rocket. So this is really rarely used, and most of the time when it's used, it's being misapplied to a situation it isn't in. So here you go, my least favorite force. Please don't use it. So lastly, this is kind of just a segue into Physics 203. There are electric and magnetic forces, and they are complicated. But luckily, we spend an entire semester studying them. Now, these are long-range forces, and yeah, they're kind of complicated. So there's going to be some situations in this class where we might refer to a situation where there is an electric or a magnetic force, but you're just going to be told something about what that force is, or you're going to be calculating its strength or direction. Next semester in Physics 203, we will actually study, well, where is this coming from on a fundamental level? So the details right now of how these work, we are not doing them. It takes a whole semester to get through it. Here's a picture to give you a little preview for what's coming in the spring. But part of this is also showing you that what you're learning right now in Physics 202, things like forces, velocity, acceleration, right? This picture, which has magnetic fields and forces and charges, still has velocity vectors. And if you look, this looks like uniform circular motion, because it is. And energy will be the next big topic that we study in this class, and that's hugely important next semester as well. So everything that you learn in Physics 202 is really important for Physics 203. And depending on what you're interested in, I know for some people you might be interested in, engineering or maybe neuroscience, where actually electric charges, electric fields, electric potentials are things that you're really interested in. But to understand them, you actually need to know everything we're talking about right now.